After going through, please be quiet, voices off, up here, let's look. Investigations into the photoelectric effect in hydrogen's bright line emission spectrum revealed that light could behave as both a wave and a particle. Now, looking here, the photoelectric effect is shining light on metal, and then the metal ejects the electrons. Einstein did experimentation with the photoelectric effect, and only certain wavelengths of the light were able to eject those electrons. Like reds were not high enough energy, but we know red have longer wavelength. They are not as high in energy. Something like the blue up here, though, 450 nanometers, that was short enough of a wavelength that had enough energy, enough quantized amount of energy in order to eject the electrons from the metal. So these two experiments, Bohr's line emission spectrum, Einstein photoelectric effect, allowed for the idea that not only does, that wave behaves as a particle wave duality, that light can behave in either way. It can behave like particles, it can behave like waves. So, moving on. Electrons as a wave. De Broglie showed that electrons, which are particles, could actually exhibit properties of waves as well. So further along now, we have the translation. And not only waves have particle, not only light has particle wave duality, so do electrons, particle wave duality. So they have the ability to be either property, they can behave like particles that can bump into things, they can behave like waves that are like energy. So it's kind of an interesting combination here. Now, evidence of the wave pattern you can see in the diffraction up here. Like these are like crests and troughs here, okay? Up and down of the wave motion there, as you see, okay? Heisenberg came along and formulated the uncertainty principle, which states that it's impossible to determine simultaneously both the velocity and position of an electron. So electrons are very small, and when you try to detect where they are, you end up moving its position. So, and it also, if you hit it with something to find out where it is, where its location was, once it's no longer located there, now the speed of the particular particle, like an electron, is no longer the same either. So Heisenberg brought in the idea of probability here. And we don't actually know specifically. You can ask it where it is, the electron is, but then it moves. So you're never going to know specifically the position and the velocity at the same time. Brings in the idea of the probability here. So this picture is showing you a gamma ray hitting the electron to establish its location, but as you can see, when it finds its location, it bumps it, and now it's no longer in that location, and it's probably now moving at a different velocity or different speed. So keep that in mind. Now, the quantum mechanics, Schrödinger developed a formula to treat electrons as waves. His equations only have certain solutions, certain quantized energy levels. You do not need to know this equation, but it is a very complex equation, as you can imagine by looking at it here. The idea, though, is that he puts the charges, the masses, and all that stuff in the equation, and he cranks out these solutions. And these solutions tell us, and it's a lot of, higher level math where you take these solutions, you graph them, and then you get these three-dimensional areas on the graph. So the solutions to the Schrödinger's equation are known as wave functions. And you guys heard of functions from math. You put functions into your calculator, and then when you get to calculus, then you have areas under the function and graphs and so forth. Like I said, you're going to establish a particular area. Three-dimensional space is what his wave functions were able to calculate, and those particular areas are going to be the orbitals of where the electrons are going to be placed, or where they're going to be residing. where the electrons are in the cloud. They all have their own specific orbital as to where they're going to be located. Now, the thing about that, though, is that the wave functions only give us a probability. Once again, Heisenberg and Schrodinger gave us this idea of probability of finding an electron in a certain amount of space around the electron cloud. The electrons do not travel around the nucleus in neat orbits as Bohr suggested. Instead, the electrons exist in the three-dimensional regions of space around the nucleus, which are known as orbitals. And the orbitals, the most likely location of the electron, is going to be where we're going to be placing them when we do electron configurations and when we do orbital diagrams. You're going to know what those are in another day or so. Okay? What does an orbital look like? This specific orbital is an S-shaped orbital. The S orbital is a sphere, and this graphic up here is showing you an electron dot density diagram where they used things to detect where they were and asked it where it was and found the location. So over a period of time, we're able to establish. And as you can see, the majority of where the electrons, when asked where they were in the center. That is where the highest probability is you're going to find the electron. As you can see, mostly in this center area, in this round center area is where we find most of the electrons are most of the time. Okay? So we're going to be looking at it from the orbital perspective. So the Schrodinger and Heisenberg brought us the idea that electrons behave as waves and they behave as particles, and it can be calculated mathematically, although you don't have to do any of the mathematical calculations because those, of course, would be complex. So real quick, I just wanted to show you, this is the beginning of the next segment of notes. We're not going to get through it all today, but this is what we call an off-bow diagram. But in the off-bow diagram, we have things labeled as 1s, 2s, 2p, 3s, and these boxes here. And it all goes in order of increasing energy over here on the side, okay? But these boxes, because we can't draw what they actually look like and make it a reasonable time thing, we're going to be using the boxes to represent those specific three-dimensional shapes as to where those electrons are going to be likely 90% of the time. So let me show you, though, what those shapes look like so you get a good idea. They're very, very complicated, especially in the D and the Fs. Oops. It's not here. Hold on. Back. Maybe I'm pulling up the wrong PowerPoint. Hold on one second. Okay, so the shapes of those three-dimensional spaces, when we're saying like 1s, we're talking about the first energy level, and it's a sphere shape like this one up here, right here. This is an S-shaped. S-shaped orbitals are spherical, so we're going to have to know that particular shape. Over here, the P's, there's 3 orbitals in the P sublevel, and they form dumbbell shapes. You guys know, like dumbbells at lifting weights, you lift right there. So they have weight on both sides. That's the idea of calling them the dumbbell shape. But there's 3 boxes on the P sublevel because there's 3 orbitals, and when each box, like this would be the first box on the X plane, the second box in the P orbital is going to be the box on the Z plane, and then the third box of the P orbital is the dumbbell shape on the Y plane. So that's what we're looking at when we're doing the boxes here. We're really placing them in these three-dimensional spaces that you see up here. So like in the D, this would be the first box, this would be the second box, the third box, the fourth box, the fifth box. And where you're putting your electrons is which three-dimensional space are they going to be likely to be 90% of the time. So we're going to be talking about that and looking at it, and we won't have to draw these shapes because they're kind of complicated. But we will be using the box system to represent in place of drawing these shapes. Because when you place an electron in here, you're really placing it in one of these three-dimensional spaces around the nucleus. The nucleus being in the center, of course, of the orbital there. Okay? Now, we're going to look at the dinner party.